Welcome everyone. My name is Praveen Rokaya. I'm the science coordinator of the Global Water Futures Core Modeling and Forecasting team. It is my great pleasure to welcome you all today to the topical webinar on advances in Icejam flood forecasting. Today we have Dr. Carl Eric Linde-Smith with us. Carl is an associate professor at the University of Saskatchewan and one of the global experts in river ice. He has recently published a book entitled River Ice Processes and Ice Flood Forecasting, a guide for practitioners and students. Carl's method to ice and flood forecasting has been adapted for the Churchill River in Labrador, which, to my knowledge, is the first fully automated real-time ice and flood forecasting system that has ever been implemented for operational use in the world. I believe Carl will be highlighting it today. Without taking much time, I want to kick off this webinar by thanking Carl for graciously accepting our request to share some of his knowledge, expertise, and experience. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Carl, the floor is yours.
Thank you very much, Pravin. Yes, so as Pravin has introduced it, my talk is on advances in Icejam flood forecasting. And I do want to also spend more time on a particular method that I've been developing and extending over the years. But first, what I'd like to do is maybe just quiz you a little bit. I like to do this with my students just to get them primed for the subject of ice jams. Here is an ice jam in Winnipeg along the river. Can you tell me what the flow direction is? I'll just give you 5 seconds for that. So here's an intact ice cover here. This is the intact ice cover. The flow direction is actually this way from top to bottom. And here we have an accumulation of ice, and that ice rubble will flow and lodge against this ice cover, this intact ice cover. And due to the increased discharge and resistance to flow, you will get backwater upstream of the ice jam, and then you can see some flooding over here. Here is a plan view of another ice jam. I'll give you 5 seconds if you can, just to determine what the flow direction is here. This is a little bit more complicated. The flow direction is actually from right to left. So here we had actually an initial ice cover here, and this rubble here flowed downstream and abutted against that cover, and then this cover released, and you can see here this arcing here is strong enough to maintain the structure of this jam here. And then you can see the rubble here is a little finer. It's probably from further upstream and was released in a different, perhaps another ice cover or ice jam at a different event. But when it ended up here with this jam, that accentuated the backwater staging. And then you can see that some of these houses here along here got flooded. This is here the ice jam flood event from 2020 in Fort McMurray. We see here the Athabasca River, and here's the Clearwater. Just to give you some perspective here, I'm going to show you just a map of this. So the photo I just showed you is from this direction here. This is the downtown part of Fort McMurray. Here's the Athabasca River here, and the flow is in the northern direction. And there's a transition from a very steep area here down into this more flatter lowland area here. And the ice that flows downstream does get hooked up in these islands here, and what can cause jamming. And then you have the discharge being blocked, but then backfilling or backflowing in up into the clear water, which is river, which is quite flat, and will then flood this town of Fort McMurray, which is situated on the floodplain of Clearwater River. Yeah, so lots of damage, lots of it's just a huge issue for some of the northern rivers. Just want to show you too just how the processes are with the ice jam formation. Here we have our intact ice cover, and then we have ice rubble flowing downstream and lodging at the ice cover here, and this will cause this water level to increase in height, in elevation, and when you get more ice rubble coming down the river and lodging on that already existing jam, your backwater levels increase even more. Yeah. Now this is here the toe of the jam, and the toe of the jam will also, depending where that is, can change the morphology and the backwater staging of your ice jam as well. So it becomes a chaotic process in essence, yeah, depending on how much ice comes in, how much, what your discharge is, the location of the toe, and other variables as well, which will then determine the morphology of your jam. We'll be able to see this here. Here I have a discharge water level curve here, discharge on the x-axis, water level on the y-axis. And this is here now just for an open water case. You can see it's quite smooth. This is sort of a rating curve, quite smooth. These are annual maximum water levels for certain discharges along. This is for along the Peace River at the town of Peace River. Now, ice jamming is a different story. It doesn't quite fit like this. So here are the maximum water levels for certain ice jam flood events, and I got the years here as well. One thing you'll notice is that the discharges to cause the flooding are substantially lower than for your open water floods. Yeah. And if you take a look, for instance, these two extremes here, 92 and 97, they're actually almost very similar in discharge, in water level elevations. But the 92 one is half the discharge of the other. Yeah. I've also put on here the daily mean of these, and maybe just to show you here, if we take 1 day, for instance, this is stage or your water level elevation, and if we have recordings, many recordings throughout the day at certain intervals, it's be it 10 minutes or half an hour, you can add those up and take an average, and that'll be your mean. However, for ice jams, we like to take this instantaneous maximum, because that's the because very often these jams will occur within a day. They will have a certain rise in your staging, and then there will be a recession as well, and that makes them also quite dangerous. Yeah, the flashiness of jams, and difficult to predict and to forecast. Yeah. Okay, now there have been previous attempts for forecasting. There have been empirical approaches, neural network, fuzzy logic approaches too, also deterministic multi-model approaches as well. I too like to use a deterministic model for a basis, yes, but I embed it into a Monte Carlo framework, and with that, this is probably the novelty of the method, is that I calibrate that framework, not using specific values of your boundary conditions or your parameters, but I'm calibrating frequency distributions. Yeah, so I'm working a lot now with frequency distributions and not single values of a parameter or a boundary condition. And so this is the outline of my talk. I'll go through this. First, I'll go with the model description, the model that I use, which is Riv Ice. It's a fully dynamic model which incorporates many of these ice processes, not only for breakup jams, which I'm going to concentrate more in this talk, but also for freeze up too, and border ice formation, anchor ice as well. And I'm going to look more specifically at wide jams, where we're looking at a balance of forces, where we have, let's say, the thrust of the discharge of the flowing water against the front of the jam. We also have the resistance to flow on the underside of the cover. And also in the sloping direction, you also have a weight component here. And that will be offset by forces of friction of the ice cover along the bank. And if there's some freezing, there'll be some cohesive forces. And then also due to the thickening of the jam as well, some internal resistance to those forces. And if we look at the balance, if these forces on the jam here, the thrust, weight, and drag are higher than the other ones, you will get a certain shoving of your ice cover against your jam, which will thicken it and also increase your backwater staging. But you can have also the situation where these forces here on the left do not outweigh the ones here on the right, and you will just probably get some more just juxtapositioning of that ice cover, the extension of that ice cover in the upstream direction. We also have a lot of parameters. I'm not going to go too much in detail into those, just maybe specifically just to say there's some thicknesses of your rubble or your front, porosity of them as well here. There's some roughness coefficients and velocity threshold coefficients as well, thickness of your downstream intact ice cover. But what I really want to concentrate here in this talk is the volume of ice, the volume that comes downstream to form your jam, your discharge as well, and then also the location of the ice jam toe, which can have a big impact too on the morphology of your jam and your hydraulic regime. And so first, before we can go into the framework, we need to calibrate our model as a deterministic model. I already went into a bit of the study site here at Fort McMurray. And our model domain, I'm just going to concentrate here on the Athabasca River. So from this point here, our upstream boundary here, and then our downstream boundary here as well. And here is a jam, 1979 jam, a little older. Those were the days when a lot of these, there was a lot of detailed studies undertaken after such flooding events. So they're quite useful data for model calibration. And I typically, orange is my riverbed, and the black here is my ice cover, my ice jam here. You can see this, the lodging is right over here. These red dots are the high water marks that were observed. I like to put it in a blue. This blue line here is the equivalent, is the open water profile for an equivalent discharge. Yeah, so this just gives you an indication of the staging that occurs through the ice cover and the ice jamming. So there we've got about 5 or 6 meters of staging here. And we'll do various jams. This is the 97 one here, was also quite a heavy flood year. And then also the one in particular last year, 2020, we also did the simulation of that jam as well. And this gives us a range too for our parameters that we need to use. This is now for our stochastic framework. So here we have similar what I showed for the Peace River. See, this is our jam events here. And you can, of course, group these, bin these into a histogram. Now this histogram is rotated a bit just to get my point across here that these events are now binned here in this histogram. And now you wouldn't want to fit a normal distribution. I mean, you could, but with a normal distribution, you're actually going to miss your extreme values here. And these are the ones that are of interest to us, or are particular of interest to us. Yeah. So what you need actually are in the extreme value distributions. Yeah, such here. And I've just rotated that back, that histogram 90 degrees clockwise. And you can also, to show you that you can represent this frequency also as a frequency distribution here, where you have exceedance probability on the x-axis and your water levels here on the y-axis. And this is what I've done here for the instantaneous maxima of the Icejam flooding here for the gauge at Fort McMurray. And now coming to the volume of ice. This is a very difficult condition to determine. What is this volume of all of your ice jams, let's say, of the last 40 or 50 years? What is the distribution of that? The location of the ice jam toe is also fairly difficult. In this example, in this talk here, I'm just going to assume that it's a uniform distribution along a certain length of the river. And Q is can maybe be better estimated, what those flows were approximately when those ice jams occurred. And I'm going to show these here. These are your distributions. So this is for flow. I said for the location of the ice jam toe, I would use a uniform distribution. And same with the parameters. Parameters having a certain range, a minimum and a maximum. And what I don't know is this volume of ice here. So, and for that gauge, at that gauge location, I do have observed data. And that observed data, I can form a stage frequency distribution. So I'm calling this the observed one here. This is my Thalweg here. So I'm going to make an initial guess at my volume of ice. I don't know what that is. I'll take a guess what that is. And I will then from each of these distributions, randomly pick values from them. Then do a model run, and I'll get a backwater profile. Then I'll do it again, pick random values from each distribution until I get my 40 or so profiles. And then at that gauge location, I will then extract my water levels and then do, I'll call it a simulated stage frequency distribution, and see how well that coincides with my observed. It doesn't here. The simulated is higher than my observed. So what I'll do is I'll go back and I'll adjust my distribution for my volume of ice and do the process again. And I'll do that so many times until my simulated profile coincides with my observed stage frequency distribution. Yeah, and this is what I'm calling I'm calibrating this framework using stage frequency distributions. It's a calibration of frequency distributions. Okay. Here's now in actual simulations of the ensemble here, and this was the observed and the simulated. And I'm going to, with that same distribution, because it's all random numbers, repeat it many times until I get an envelope of simulated stage frequency distributions, and just to make sure that the median of that approximately runs along the observed stage frequency distribution, and just to make sure I'm certain enough about if I'm getting the right distribution. And I'm quite happy with that, and this is what ends up to be my volume of ice distribution at that gauge at Fort McMurray. So now we've got it calibrated, our framework. So now let's put it into a forecasting context. And for this here now, I need forecasted flows. And in this particular example, we used the hydrological model MESH, and this work was actually carried out by Prabin for his PhD, and he was able to give us 10-day forecasts of flow for the Athabasca. So here we have a digital elevation model of that basin. The gauge at Fort McMurray is right here. Yeah, so this is the clear water here on the right, and then the left here is the Athabasca. And we see here our grids for our mesh model. And we, of course, have to do also calibration and validation, but we have to also do a more fine-tuning of the calibration to fit it better to our more winter conditions. So we did have some values for the under ice discharges as well. It's very difficult here sometimes to calibrate this breakups situation. Yeah, it's neither open water nor intact ice cover, and so it's quite difficult to determine what your discharge is here. But we do some estimations for that. Now, one thing I don't know is I don't know the exact date in the future when that jam is going to happen. Yeah, could happen in 3 days, and 5 days, 10 days from now. I don't know. Yeah. So what I'll do is I'll do a 10-day forecast of my flow. This is forecast 1. I'll do a 10 or 9 days here, and I'll look what my maximum and minimum is. My minimum flow and my maximum. I'm going to have a range here. And with that, I'm going to constrain my discharge distribution. I'm only going to take a certain range within it and pick random values from that, yes, to do my runs. The volume of ice I can also constrain, especially when the when the breakup persists, it's continuing, and your ice front progressively moves downstream and approaches your area of interest or your gauge location closer and closer. Then that ice upstream of your potential ice jam area becomes shorter and shorter, hence also the potential volume of ice becomes less and less. So that's why I'm showing here some constraining as well here. Then we'll do an ensemble run here, and then also do a frequency distribution. and to see probability of exceeding a certain flood threshold. We can also do that, create maps. So we'll do many maps, maybe 100 or so, depending on time. For forecasting, you have to do this like once a day. You want to get out a forecast once a day, so there's quite a lot of steps to go through. So you might only be able to do 100. So 100 maps, and from those 100, you can then count from your DEM how many times a cell is flooded, and you can get a probability of flooding. And we did 6 forecasts. This was for year 2018 when we were first developing this method. And we had some photos. It's very hard to verify how well your forecast did, but we did. There was some flooding in the town. You can see here where it's the wetted areas here, and helped us to verify our forecasting system. Now, this while this was being developed, this was in partnership with folks from Alberta Environment and Parks, but also from the government of Newfoundland and Labrador. And in Labrador in 2017, there was an extensive flood event on the Churchill River. That's the Atlantic Churchill River. This mud lake and parts of this mud lake access point were flooded from that event. And it was decided from that to develop a Icejam flood forecasting system. Here are some pictures of that event here. This is the Churchill River here, and then there's a side channel here. You can see the town where it was flooded out. Here I was able to model some events quite nicely, actually. And in this case, I also had the downstream water level being this is tidally influenced here. There's a connection here to the Atlantic Ocean here. So this is influenced by tides. And also here I've shown this already constrained, and they actually wanted more showing our ensembles more as percentiles, 10, 50th, and 90th percentile. And I'm going to show this now. Let's see here. So it's all automated. Everything's loading right now. I just logged in. We have all our gauges, readings all the data feeds are automated as well, and also forecasts. Now, we don't have ice on the Churchill River right now, so this is in real time. This is as we are, so it's only an open water modulus. So it's using HEC-RAS open water to do the forecasts, the backwater level forecasts. There's some maps here. We'll have precipitation the next 2 days, same with sort of the average temperature. And of course, we don't have ice right now, but I'm going to go back now to this for ice condition. This is now May 11th, 2019. There's a link to spaceborne remote sensing, where we also then get the data of our ice cover. And this has to also be used as data in our forecasting system. And we do have, this is the forecast board. That's the dashboard. Sorry, that was the dashboard. And then we also have other tabs here for notifications, diagnostics, making sure our models are running correctly, configuring the system, and also forecasting here as well. And here, these is the flows that have been forecast in the next 3 days. And here is the water level, those percentiles, 10, 50, and 90 percentiles of our anticipated backwater levels of the ice jamming. And that can then be plotted out too as a longitudinal profile along our study site from Muskrat Falls down to Lake Melville here. Okay. Yeah, so that's it's fully operational in real time, and it's running all the time, actually, both winter and summer, not only for ice jamming, freeze up and break up ice jamming, but also open water floods as well. I'm just looking at the time. I'm actually doing pretty good here. We're also working with Manitoba Infrastructure to extend their forecasting capabilities of ice jamming along the Red River, and particularly the lower reach of the Red River. This is here, Winnipeg here, and we have Selkirk here, particularly between the area between Selkirk and Lake Winnipeg is prone to ice jamming. You can see here. And we have also a bit of a difficulty here that there is also, this is becoming also a deltaic area here, quite flat, quite low banks along the rivers, you can see. And we have this, some people are prepared for that flooding here. We have here dikes around the house here, others not, yeah. And here we have simulations. This is the thalweg of that lower part of the Red River. And we have here in red the 10th, 50th, and 90th percentiles. We also have here some of our bank elevations to see where we could have our potential flooding. Manitoba Infrastructure also likes to have us do the ensembles as well without ice, just to see what the open water conditions would be, and also to see what the increase in staging is due to ice jamming and ice processes. And here's an attempt to measure the skill of a forecasting for this year. This was 2019. The ice jam actually occurred on the 11th of April. And that's the observed here. But here, the bars here is actually what we forecasted 5 days previously. Yeah. So actually, we're doing very good here. But you only do well if a jam occurs. That's still a bit of a research question. When will that jam occur? So we start early enough to see what the potential jamming might be. And when the actual jam occurs, then we can see how close we were to the observed. This was actually a fairly good result here. And we're also extending this the St. John River. So this is in Atlantic Canada here. And we're looking first at the upstream part here, upstream of the first dam at Grand Falls. So this is more naturally flowing stretch here. We also want to extend this to more the regulated part here. The next dam is at Beechwood and Mactaquac as well. But for first shot, we went for the headwater part, and we're able to simulate those jams quite well. This is also on data that was previously collected by Spiros Beltos from Environment Canada. He's helping us a lot on this Icejam research for the St. John River because of his experience with it. And here too now ensemble of Icejam simulations, which can then be translated to a set of percentiles as well. Some more spin-offs of this framework. We've been also, I can't go into all detail on this. There's papers on this that if you're interested, you can let me know. I can share those with you, but we're doing also flood risk mapping, not just hazard, but also, including the annual expected damages and to assess certain mitigation options. It also allows us to help what I've coined the probable maximum Icejam flood, just to see what potentially could be your maximum staging for a certain reach. Also looking at impacts of climate change, and particularly for the St. John River, looking at midwinter Icejam flooding and how that also might change. Forecasting that has its own particular set of challenges and difficulties, and also wanting to extend that in the future to see how though that might change with climate change. Yeah, and if you want to know a little bit more about this, you can. Pravin said at the beginning, there is a book on Icejam, ice flooding, I call it ice flood forecasting. Includes tutorials with data sheets and models and step-by-step videos to help you get accustomed with some of these details that I've gone through here at my talk. And with that, I'll give it back to Pravin, and thank you very much for your attention.
Thanks, Carl. That was fantastic. Now we'll be moving towards a Q&A session. I'm looking at the questions. So one of the questions that we have is from Chiranjeev, and he asks, it is possible to do the Monte Carlo simulation with the flooding extent as the target, like use of CSI or similar index?
That's also future work. I actually want to couple the Riv Ice model to a 2D floodplain model, sort of like a lease flood approach. It's a European model where there is a coupling between a channel 1D model and I think they use storage cells 2D configuration in the floodplain with interaction with water flowing to and from the channel into and from the floodplain. So that's on our list, on our to-do list.
I have one question. So I'm just wondering about the correlation in the parameters, and have you considered doing sampling, using the joint probability distributions, because now we are sampling independently all the parameters, right? So have you considered that?
Yes. I mean, that's one thing you have to watch too with the boundary conditions is with this method, making sure that there is independence, between the distributions that you're using as input, and we also have a paper or two on that where we specifically explore that.
His comment from LB, and it says, great presentation, Carl, thank you. I wonder what your high-level thoughts are on climate change impact on the intensity and frequency of Icejam floods.
It's very difficult to say at times, because I find right where, yeah, it's that transition at breakup. Yeah, it brings in a lot of uncertainty in our climate change, the impact of climate change on ice jam flooding. So I find, because let's say, I mean, let's say you get more winter precipitation, less summer precipitation. Yeah. I mean, those are quite distinct characteristics, but it's that transition at spring breakup. You don't know really, there's a lot of uncertainty there. Will the flows be a bit higher, or will they be a bit lower? I don't know. Sometimes it's difficult. So I find it's most challenging actually with the predicting how ice jams will behave in the future for certain riverine systems. Yeah, just because of that issue.
We didn't talk much about the midwinter jams, but that will be something that's that affected by the climate change, because as you see more warming in the winter period, you might get more midwinter breakups events. So do you have any thoughts on that?
Yeah, so which can make actually the situation more severe. Yeah, so with increased midwinter breakups, midwinter breakups can almost be more detrimental than your spring breakup jams, because very often you do have, retain freezing after the jam. You have these, very often the midwinter breakup occurs if you have a sort of a flash heating event, high temperatures, and you get some rapid discharges, so it breaks up the ice and cause jamming. But that heating can be temporary, and you get a lot of that freezing now, and very often that stays in place, that freezing, until the spring. Yeah, so and if those become more frequent, then you could actually be in a worse situation than we are today. Yeah.
There's another question from Jim. He says, what is going to advance the science from here? Is it improvement in the observation for validation? And what is the potential for measuring backwaters with satellites such as ICESat? Sorry if this was the first part of the talk. He was a little late, so.
So one thing we'll never be able to, one thing that will always have to be included in this forecasting is the continuous monitoring of your ice cover, and how that ice cover is continuously moving down river. You have to know where that ice front is, because a lot of that also determines your parameterization for your flood forecasting system. And while we were doing this, remote, you can't always fly. You can't always depend on aerial surveys. Spaceborne remote sensing is great. However, we found that they just weren't fast enough or not frequent enough. We get an image, every 2 or 3 days, just not enough. You really need something every day. You need to see what the ice cover looks like on the river every day. And I think it's improving now. Now we don't have RCM, so we can draw on that. So I think we've made some big strides there. But you can always improve on that. I think that kind of monitoring information is valuable, is key for forecasting. So that's improved a lot, and And I think that there's always more room for improvement in that area.
Yeah, and also I think so. We have recently written one paper which is in revision, and we are for modeling ice and floods under the past and future climate, where we also try to discuss some of these things like what should we do in terms of process, process understanding, which processes are not clear, what should we do in terms of parameter sampling or modeling, or what we should do in terms of community, where should be our focus, something like that. So there's one section that we have written, so hopefully we can get it out through the system soon. Okay, so there's another question. So all this knowledge that you are generating, is this being forwarded to the end users or stakeholders or local government?
Is it
The,
being
the
conveyed?
knowledge, the forecast, the data, the information?
Oh yes, yeah. I mean that's one reason I brought out this book, is to um, in detail show how these processes work in a forecasting context. I've been working with Manitoba Infrastructure, Ben Luo and Chris Prop. I've been working with Ali Khan and his group at Government of Newfoundland and Labrador. There's just a lot of other projects. I just highlighted those three, but there's other projects too that are using this method, this framework, not only for forecasting, but also, which I alluded to, as the Icejam flood risk assessments, that mapping, and also climate change impacts as well. So we're doing a lot of work with end users and other folks that work in forecasting. It's usually provincial governments, of course. They're the ones that have the mandate for forecasting. And for maybe at some point when we have the water agency, the federal water agency, it'll be broaden out into more of a federal mandate.
Yeah, and just to add that also that the dashboard you showed before was for the government of Newfoundland and Labrador, who was adopting the forecasting work that you were doing in the Churchill River. I don't see any more question. I'll just give 5 seconds. Okay, so there's one question. So it's from Lauren. Do you have sense how United States handles Icejam forecasting?
Do you have a sense of how
they do in US Icejam forecasting?
Well, I just find, well, it's a bit of a sensitive question. Well, I do have now a project with a prof at the University of Alaska at Fairbanks and the National Weather Service in Anchorage. We're looking not on the Yukon River. It's, oh man, I always forget the name of that river. It starts with a K. It's the second largest river in the Yukon. We're looking at, we have a project now together, the three of us, and also the community members along that river, to develop the Icejam flood forecasting capabilities for that river. And we're going to, I'll be going out there next winter collecting data, and hopefully within a year and a half we'll have those capabilities up and running for forecasting Icejams along there. We also had some interest too from some of the power providers along that river as well. So it looks like it has a lot of potential to bring in a lot of groups, different people, and end users. So yeah, that's that's our expansion into the U.S. Yeah, so I hope that answers your question.
But are you aware if nationally or at the state level, US has some kind of like Icejam forecasting system?
Not to the extent that I've made it here. Yes. I've also been trying to get this going also on the Oder River in Europe. The lower part of that river forms the border between Poland and Germany. So there's interest there. And we just, with another company, we put in a proposal with the European Space Agency to look at a river that borders Sweden and Finland. So looking at extending the capabilities there. So I don't know anybody else that has brought it this far, the Icejam flood forecasting. But there's a lot of interest, and hopefully people will pick up on it and improve on it. Yeah.
Yeah, I don't see any more question. I'll just give everyone 5 seconds if they have any quick question. If not, then we'll be ending towards the conclusion of this webinar. All right. Thank you again, Carl. And I also want to thank everyone that attended this webinar. The video recording of this webinar will be available later today in Core Modeling website. Just a note that next week we'll be having a presentation on hydrological modeling in high mountains of Central Asia by Juha He from the University of Saskatchewan. So please stay tuned. That will be all for today. Thank you again. Please stay safe. Have a good day.
Thanks, Pravin.